Right, so in this video I'm going to run through Le Chatelier's principle and how changing temperature and concentration and pressure can affect the position of equilibrium. And once I've done that, I'm going to have a look at how those things can, or if they affect the equilibrium constant. So again, I've got your standard reversible reaction, the Haber process. And here I've included that the enthalpy change for this reaction is minus 45. If you're given the enthalpy change value, it always refers to the forward reaction. So this tells you that the forward reaction has an enthalpy change of minus 45, or in other words, the forward reaction is going to be exothermic. If the forward reaction is exothermic, then the reverse reaction is going to be endothermic. So the forward is minus 45, the reverse will be plus 45. So that is important information when you're trying to figure out what effect on equilibrium increasing or decreasing the temperature will have. So we'll just have a look at that here. Okay, so if I increase the temperature, what's going to happen to the position of equilibrium? And by position of equilibrium, I mean, is equilibrium going to lie to the left? Are you mostly going to have reactants when equilibrium is reached? Or is equilibrium going to lie to the right and you mostly have products when equilibrium is reached? So if you increase the temperature, according to Le Chatelier's principle, anything you do to the reaction will try and do the opposite. So if you're increasing the temperature, what the reaction, which I'm just going to abbreviate out to RXN, the reaction is going to try and decrease the temperature. And if it wants to decrease the temperature, then the endothermic reaction will occur. And if you think about that, that makes sense, okay? Endothermic reactions, they absorb heat energy from the surroundings, and the temperature of the surroundings decreases. So if you increase the temperature to decrease the temperature, again, the endothermic reaction will have to occur. And we know that the forward reaction is exothermic. That means the reverse reaction must be endothermic. So the reverse reaction is going to occur, and I can say that the equilibrium or equilibrium position goes to the left. If you decrease the temperature, again, the reaction will try and do the opposite. So the reaction will try and increase the temperature again. And if it wants to increase the temperature, then this time the exothermic reaction will occur, okay? Because exothermic reactions release heat energy to the surroundings and they increase the temperature of the surroundings. So we know that the forward reaction is exothermic. That means the forward reaction is going to occur. And if the forward reaction is occurring, we say equilibrium shifts to the right. The next thing I can do to change is change the concentration. So here I've said I'm changing the concentration of N2. I'm going to increase the concentration of one of my reactants. So if you're increasing the concentration of N2, the reaction is going to try and decrease the concentration of N2. In other words, it's going to try and use up all of that N2 that you've just added to the reaction flask. And if you're trying to use up the N2, then the forward reaction is going to have to occur and equilibrium moves to the right. So if the forward reaction is occurring, which is this one going from left to right, there's my forward. If the forward reaction is occurring, then the N2 is getting used up and the concentration of N2 will decrease. If I increase the concentration of H2, the exact same thing would happen. If I increase the concentration of NH3, then the reaction would try and decrease the concentration of NH3, and the reaction would end up moving to the left to use it all up again. What I've written down here, though, is if I decrease the concentration of NH3, what will happen? Well, we know if we decrease the concentration of NH3, the reaction is going to try and increase the concentration of NH3. And if I want to increase the concentration of NH3, then I need the forward reaction to occur and I need to move to the right. And this is quite a helpful piece of information. Like the Haber process is something done on a large industrial scale. And if you're trying to make more ammonia, I mean, you don't want to have to add more reactants. That's just costing you money to have to put more reactants into the flask. So increasing the concentration of N2 is not particularly viable going forward if you're doing it on a large scale. But this, decreasing the concentration of NH3, you're effectively just taking the ammonia out as it's being formed. And by removing the ammonia as it forms, you continue to promote the forward reaction and you'll continue to make ammonia to replace what you've taken from the flask. So it's a great way of increasing your yield of ammonia. Another thing we can do is I could increase the pressure, all right? Again, if you increase the pressure reaction will try and decrease the pressure, all right? And if you increase the pressure, what you're actually doing is you've got less space. So you've got the same number of particles, but you've got them in less space. So what the reaction will do is it will move to the side with the fewest gas molecules. So if I look on the left, I've got 1 N2 and 3 H2. So I've got 4 molecules of gas on the left-hand side. And on the right-hand side, I've just got 2 NH3. So I've got 2 molecules on the right-hand side. And if I increase the pressure, the reaction tries to decrease the pressure. And it does this by moving to the side with the fewest number of molecules, okay? Because you're after creating an area where you've got less space. So if you had less gas particles in that smaller space, then the pressure wouldn't be as high. So the reaction is going to move forward. Equilibrium shifts to the right. And then the opposite is true. If you decrease the pressure, the reaction tries to increase the pressure again. If you're trying to increase the pressure, it will go to the side with the most gas molecules. And in this case, that will be the reverse reaction that will occur, and equilibrium is shifting to the left. This here pressure only applies if you've got gases. So it's only going to be relevant to a reaction where everything's present as a gas, and it is in the Haber process. Also, if you have the same number of gas molecules on each side, then changing pressure wouldn't affect equilibrium at all. You have to have a different number of molecules on each side for pressure to have an effect on equilibrium. The last one I've got is catalyst, and a catalyst has got no effect on the position of equilibrium. A catalyst will affect the forward and the reverse reaction equally. It doesn't have a preference regardless of the reaction, so catalysts are not going to have effect on the position of equilibrium. So that's just a kind of a recap of Le Chatelier's principle, which you cover in more detail in chapter 10. But in chapter 19, 19.3 focuses on how these kind of changes in temperature and concentration and pressure, how those changes will affect the values of your equilibrium constants. So in the previous videos I've made, we've looked at calculating the equilibrium constants. We've looked at Kc, which deals with concentration, and Kp, which deals with pressure. In this video, it doesn't matter if I'm talking about Kc or Kp. Everything I say is applicable to both. So I'll just firstly remind you what do these constants actually mean. If you calculate a value of Kc, if you calculate Kc and it's got a value of 1, that means that when equilibrium is reached, you've got a 50-50 split between your reactants and products. If Kc is greater than 1, then equilibrium lies to the right and you've got mostly products in your flask. If Kc is less than 1, then equilibrium lies to the left and you've got mostly reactants in your flask. So what I've got here is a reaction between high hydrogen and iodine. And what I want to know is if I increase the temperature, well, what's going to happen to my value of Kc? So before we kind of, plug any numbers into the equation and write ourselves a Kc expression, we can just, predict what we think is going to happen here. So I've given you a reaction, and again, I've told you that the enthalpy change for the reaction is minus 10.4, and this value always refers to the forward reaction. So my forward reaction has a negative enthalpy value. That means my forward reaction is going to be exothermic. Okay, and if we're increasing the temperature, we can just predict. We know if we increase the temperature, that the reaction is going to try and decrease the temperature. And if the reaction is decreasing the temperature, then we know that the endothermic reaction will occur. If you're trying to decrease the temperature of the surroundings, the endothermic reaction is going to occur. We know the forward reaction is exothermic. That means the reverse reaction must be endothermic. And if the reverse reaction is occurring and equilibrium is shifting to the left towards the reactants, then we would expect that value of Kc is going to decrease. Okay, so that's what I would expect to happen here, that the value of Kc would decrease. I'm moving towards the reactants because the endothermic reaction, which is the reverse reaction, is going to occur. So we can have a look at, kind of what this would look like in practice. So I'm going to write an expression for Kc. I'm going to say Kc equals, when I'm writing my expression, it's C, so it's concentration. So I raise that to the power of 2, so there's my products. And then I put in H2, and I put in I2, and there's my Kc expression. And let's just say we put numbers in. We put numbers into this. So I'm just going to make up numbers. I'm going to say the concentration of HI is 2, and I have to square that. And then on the bottom line, I'm going to say my concentration of H is 1, and my concentration of I2, I'm just going to say is 3. All right, so if I solve that, I get 4 over 3, which works out as being 1.3. All right, so let's just say that's my value of Kc at 273 Kelvin. Okay, and then let's say I increase the temperature, and I'm going to make it 293 Kelvin. All right, and I'm going to plug in values again. So I'm predicting that if I increase the temperature, that the reaction is going to move to the left. Okay, the reverse reaction is going to occur. And if the reverse reaction is occurring, then my concentrations of my reactants is going to increase, but the concentration of my products is going to decrease. So I've got the same Kc expression, but the concentration of my products should decrease if the reverse reaction is occurring. So I'm just going to say that I've got 1.5 squared now, when I originally had 2 squared. And again, the concentration of my reactants, that should be increasing if the reverse reaction is occurring. So instead of having 1 and 3 like I did before, let's just say I've got 2 and 4 this time. All right, and if I plug in those values into my calculator and solve, I get 0.281. So this is as I predicted, all right? If I'm increasing the temperature and the endothermic reaction is occurring, which in this case is the reverse, I do end up with a lower value for Kc when the reverse reaction occurs. And they have in the book a little study tip here that you can learn, okay? So we're talking about increasing the temperature. We said the forward reaction was exothermic in the example we just looked at, meaning the reverse was endothermic. And when we increased the temperature, we saw that equilibrium did shift to the left because an increase in temperature favors the endothermic reaction, so it was going to the left, and that led K to decrease. If you had it the other way around, if your forward reaction was endothermic, if you increase the temperature, it favors that forward endothermic reaction, which means equilibrium goes to the right, and your K is going to increase. So I'll just look at one kind of question on that. They could ask kind of different styles of question on this, but here's one, all right? So they got 2 reactions. They give you the temperature, they give you the value for Kc, and they want you to use this information to predict if the reaction is endo or exothermic in the forward reaction to explain your answer. So press pause, have a go at doing that, and press play when you're ready to see the answer. All right, so I'm gonna fill this in here. The first thing I'm gonna look at is what's happening to my temperature. All right, so I can see that I have got an increase in temperature. I'm going from 200 to 400 to 600 Kelvin. And I know if I've got an increase in temperature, well then that's definitely gonna favor the endothermic reaction. For reaction A, I mean, this might not be immediately obvious to you when you first look at it, but my values of K are increasing. Over here, I've got 5.51 by 10 to the minus 8, so that's a very small number. Then I've got 1.46, and then here I've got 3.6 by 10 to the positive 2. So these numbers are increasing. I'm getting an increasing values for K. So if the values for K are increasing, okay, then I know equilibrium is shifted towards the products. Remember, a value greater than 1 shows equilibrium lies to the right towards the products, and here, as the values get higher and higher and higher, you're getting further and further towards the products. So an increase in temperature favors the endothermic reaction. In this case, it's favoring the forward reaction, therefore the forward reaction is endothermic. The other example, we're still increasing the temperature, and that always favors the endothermic, but this time we see that the values for K are getting smaller. So you're starting by 10 to the positive 4, you're ending by 3 to the minus 2. So those values for K are decreasing. And if the values for K are getting smaller and smaller, then smaller values for K shows that at equilibrium, you've mostly got reactants. So again, we know that an increase in temperature always favors the endothermic reaction. In this case, this tells me that the endothermic reaction is the reverse reaction because I'm making more reactants. And if the reverse reaction is endothermic, then the forward reaction must be exothermic. So reaction A is endothermic in the forward reaction, reaction B is exothermic in the forward reaction. And that's consistent with what we saw a moment ago when we worked out that example. Okay, so that's for temperature, all right? Temperature, changes in temperature will affect Kc, but whether it increases or decreases, well, that depends on whether the reaction is endo or exothermic. You can just learn that little box off by heart. Personally, I wouldn't. I think understanding why this is the way it is much better for you in the exam. If you get confused and you kind of start to second guess yourself if you're relying on memory. If you can rely on understanding and you can logically work something out, it just makes it a lot easier to recall under exam conditions. So they were the effects of temperature. Okay, so temperature does affect your Kc value, and again, if I'd used Kp and used partial pressures, it would have been the same thing. But what we're going to look at now is if I had changes in concentration instead. So I'm going to take this reaction here. What am I doing? N2O4, which is a gas, going to 2NO2. And this time I want to look at what happens if I increase the concentration. So if I increase the concentration of N2O4, what is going to happen to Kc? All right. Now, according to Le Chatelier's principle, if I increase the concentration of N2O4, then the reaction is going to move to the right, because it wants to use up all of that extra N2O4 that I've just added to the flask. And if the reaction is moving to the right and the forward reaction is occurring and you're producing more products, then I would expect the value of Kc to increase, okay? But let's test that theory, okay? I'm going to start by writing an expression for Kc. My products always goes on the top line, so that's NO2 squared. And then I've got my reactants on the bottom line, N2O4. I'm going to throw in some values for concentration. So I'm going to throw in 0.4 as my starting concentration of NO2. And I'm going to put in 0.01 as my starting concentration for N2O4. And I work all that out and I see that my answer for Kc works out, numerical answer is going to be 16. All right. And then I'm saying that, well, what's going to happen if I increase the concentration of N2O4? All right, so we're assuming that the concentration of NO2 is exactly the same, so it's still going to be 0.4 squared. But this time, I'm going to change my concentration of N2O4, and I'm going to double it. I'm going to go from 0.01 to 0.02. So what's going to happen then if I plug in those values? And I'll see I get an answer of 8. Okay, and this isn't what we predicted. We said that if we increase the concentration of N2O4, that the reaction should move to the right, and if it's going towards the size of the products, Kc should get bigger. So we have that written here. Okay, when Kc is greater than 1 and the bigger it gets, the more you've got on the product side. But what we're seeing here, using a Kc expression, is by increasing the concentration of N2O4, I'm increasing the number on the bottom line. I'm increasing the denominator, and if I increase the denominator, then overall I end up with a smaller number. Okay, and that's something we see, I mean, all the time. If I look at some fractions, a half, a third, a quarter, I'm increasing the bottom line, I'm increasing the denominator, but by increasing the number on the bottom, my overall number becomes smaller. So a quarter is obviously smaller than a half. So if you increase the number on the bottom, you're going to decrease the overall number, and that's exactly what we've seen here, and it's not what we were expecting. So what's actually happening? Well, essentially, when you initially increase the concentration of N2O4, like what we've done here, you lose equilibrium completely. You're taking the reaction out of equilibrium by making that change. And then what happens is your reaction is going to try and get back to equilibrium. It wants to get back to a value of 16 for Kc. And in order to get back to a value of 16 for Kc, okay, if we look at what needs to happen, I need to get from my new value of 8 back to my value of 16. Okay, because the reaction wants to get back to equilibrium, I need to get back to this value of 16. So what needs to happen in order for my Kc, I need Kc to increase to get back to the original value. And if I want Kc to increase, then I need the number on the bottom to get smaller, and I need the number on the top to get larger. Okay, because if we see, if I wanted to make my overall number bigger, all right, if I make the number on the top bigger, so I'm going to write 1 over 1, 2 over 1, 3 over 1. If I make the number on the top bigger, then I'm going to end up with a larger overall number, which is what needs to happen here. So I increase my concentration. I initially lose equilibrium, and my value for Kc, which is it's not a real value for Kc. If you've lost equilibrium, you don't really have the equilibrium constant. But if I use these values, I'll see Kc decreases. And then in order to get Kc back to where it needs to go, the bottom number needs to get smaller and the top number needs to get larger. So what actually has to happen in order for that to occur? Well, if I want the bottom to get smaller, the bottom represents the concentration of N2O4. So I need that concentration to decrease. And if I want the top to get larger, well, the top represents the concentration of NO2. So I need the reaction to go this way. I need the forward reaction to occur in order to get from 8 back to 16. And that's what we've predicted, okay? So it doesn't happen initially. Initially, you lose equilibrium and our value of Kc decreases. But to get it back to where it needs to be, that's when equilibrium kicks in. The forward reaction will occur in order to get you back to equilibrium. So I think the important thing to think about is, the particles aren't doing what they're doing because they want to obey Le Chatelier. The particles do this anyway. And he was able to write this principle based on the fact that they behave in this way. And you have exactly the same thing for pressure. If we look at an example for pressure, the same thing is going to occur. So if I take that exactly the same reaction, because they're gases, pressure applies. And I'm going to say that I'm going to increase the pressure. Okay, I'm going to increase the pressure. And if I'm increasing the pressure, the reaction should go to the side with the fewest gas molecules, which is the left-hand side. And if it's going to the left-hand side, I would expect Kc to get smaller. So that's initially what I'm expecting. Actually, sorry, I'm going to change this to Kp because I'm going to use partial pressures this time. I'd expect if it's going to the left, Kp is going to get smaller. Again, if I plug this in, if I plug in values for Kp, so let's just say I'm starting with a value of 9.6 for my NO2, and that's going to be squared. And then on the bottom, I'm going to start with a value of 0.24. And I work all this out and I get an answer of 384 atmospheres. Okay? If I increase the pressure, all right, if you think back to how you work out partial pressures, you take the mole fraction, you multiply by the total pressure, and you get partial pressure. So if I increase that total pressure, I'm going to increase the partial pressures for both reactants and products. Okay, you increase the total pressure of the reaction, you're increasing the partial pressures of both products and reactants. So let's just say I'm doubling the total pressure. And when I double the total pressure, I end up with a value of 768 atmospheres. Okay, so I've increased the pressure, but my Kp value has not decreased. It's done the opposite, it's increased. And again, we need to look at why that is. So my Kc value is after increasing. But effectively what's happened here is I've lost equilibrium completely. I don't have equilibrium anymore. It's come out of equilibrium and my Kp value has increased. I need my Kp value to decrease again. I need it to get back to the original value of 384. And if I want my Kp value to decrease again, what needs to happen to this expression here? Okay, so if I want that value to get smaller, then it's the opposite to what I had last time. I need the number on the bottom to get bigger, and I need the number on the top to get smaller. Okay, if I look at my expression, in order to end up with a smaller final answer, and that's what I need to get from, sorry, I drawn this arrow kind of going the wrong way. I need to get from 768 back to 384. I need that value to decrease. So I need the bottom of my expression, which represents the N2O4 partial pressure. I need that one to get bigger, but I need the top of my expression, which is my products. I need that to get smaller, okay? And if I want this value here, the N2O4, to get bigger, then I do need equilibrium to shift to the left, okay? I do need equilibrium to shift to the left, which is true according to Le Chatelier's principle, okay? So if we kind of look at all of this together, all right, it's not okay to say that if you increase the concentration, it moves to the right and Kc increases. That's not what happens, all right? When you initially increase concentration, Kc got smaller, and then it shifts to the right to get back to the original value. But Kc remains unchanged, okay? It changes initially when you lose equilibrium, but then it goes back to the original value. So Kc stays constant, Kc is unchanged. And that's exactly what we see down here, all right? Initially, I was predicting that Kp would decrease, but that's not true, okay? We increased the pressure. We saw that, initially we ended up at a larger value for Kp, and then to get back to our original starting value, the reaction had to move to the left, which is what Le Chatelier's principle said. But you just ended up back at the same value that you started with. Overall, Kp has not changed. So again, I can say that it remains unchanged. So temperature, changes in temperature can change Kp and can change Kc, but nothing else can. Changes in concentration and pressure, I mean, you can still follow Le Chatelier's principle, but you end up back with the original value that you started with. Overall, those constants are unchanged. And when you're answering questions on this, it is important to use those words. So I'm going to find, there's not many exam questions on this, but I found one here. And it's not obvious that it wants you to talk about Kc, which makes it a little bit harder. So my general advice would be in any of these type of questions, don't just talk about Le Chatelier, because it wasn't credited at all in this question, but to talk about your equilibrium constants. So they've given me the Haber process, as they so often do. It says temperature stays constant. Okay, if temperature stays constant, then Kc does not change. And the chemist predicts that if you add nitrogen, you increase the portion of hydrogen that reacts. Explain whether the chemist is correct. Okay. I think a lot of people in this case would have just talked about Le Chatelier's principle, okay? And you're thinking, if you increase the concentration of nitrogen, okay, if I'm increasing the concentration of nitrogen, then the forward reaction would occur. And if the forward reaction is occurring, then the H2 gets used up. So you do use more H2 if the forward reaction is occurring, because the H2 will react with the N2. So you would say, yes, the chemist is correct. And then you look at the mark scheme and you see that that's not credited, that they don't want you to talk about Le Chatelier, that they want you to talk about it in terms of Kc or Kp. In terms of which you should talk about Kc or Kp, it doesn't matter, okay, because they haven't given you any values. It is a reaction where everything's present as a gas, so you could calculate either, depending on whether they gave you concentrations or partial pressures, okay. But what I'm going to start off with is by talking about, I'm just going to say Kc. I'm going to write myself an expression for Kc, okay, so it's going to be NH3 squared on the top, and it's going to be N2 and H2 cubed on the bottom, okay? And I'm going to say if I increase the concentration of N2, then if I'm increasing a number here on the bottom, all right, remember it's like the same as going from a half to a third to a quarter. If you increase the number on the bottom, okay, then your overall value for Kc would decrease. But we've just seen that Kc is constant at constant temperature, and they've told you that the the temperature is constant. Kc is constant at constant temperature. Therefore, All right. If you're increasing the denominator, is how they say it in the mark scheme. If you're increasing the denominator, Kc will decrease. So you have to then decrease the concentration of N2 and H2 to keep Kc constant. And in that case, yes, the chemist is correct, because if you're decreasing concentration of N2 and H2, then you are using more H2, okay? And that's what they required you to talk about. They required you to talk about the numerator and the denominator. And that you can phrase it in a number of different ways, but effectively you have to talk about Kc. You got a mark for saying that Kc did not change when you change concentration, or that it only changed if you changed temperature, so there's 1 mark going for that. You got a mark for kind of saying that you initially increase the N2, so you're increasing the denominator. So in order to keep it constant, you then have to decrease the denominator. And if you're decreasing the denominator, you are going to be decreasing H2, and the chemist is correct. It's not obvious there that this was required and that you couldn't just talk about Le Chatelier. So again, I would advise you to always talk about Kc and Kp in terms of constants in a question like this, instead of just using Le Chatelier. I mean, it's never going to be wrong. They complement each other, and you're better off to just give more than giving less. There's not a huge amount of other questions that specifically ask you about this. Of exam questions, I mean, there are a few here in the little practice questions. Again, I would advise going through them. The answers aren't exactly mark scheme specific, but they still give you an idea of how you're supposed to be explaining these things.